Hey everyone, thanks for tuning in to this discussion on the inclusion and interpretation of categorical predictors in linear regression models. This is an important topic because it expands on our ability to include different types of explanatory variables in models. We've talked earlier about how categorical predictors pose a challenge in that these linear regression models that we've been exploring so far rely on the operations of multiplication and addition. And I can't meaningfully multiply a category, like a penguin having the species Gentoo, by some coefficient. 5 times Gentoo is not really meaningful. And so in this discussion, we'll see some methods for taking levels of a categorical variable and encoding them in such a way that they become meaningful components of a model. So let's get started. So here's our motivation. We've seen this plot a few times now, and we've had several questions and concerns about it. So as a reminder, the context that we're working in here, we're trying to predict or explain penguin body mass given some physiological features of that penguin. And the predictor or the explanatory variable that we're working with here is build depth. And what we've seen is if we fit a linear regression model, a simple linear regression model here through our data, that simple linear regression model indicates a negative slope. And that would mean that as build depth increases, expected penguin body mass decreases. But I don't think that aligns very well with our mental model of anatomy. So as a penguin's build depth increased, its ability to consume larger prey, eat larger food increases. And so that intuitively we might suspect would be associated with larger penguins, more massive penguins. And so let's take a look at what we're able to do today to uncover perhaps a more intuitive relationship between build depth and body mass by accounting for a categorical predictor. So again, here's that negatively sloped simple linear regression model. We see that the model suggests that as build depth increases, expected body mass decreases. That's indicated by this negative coefficient. And as build depth increases by about 1 millimeter, we'd expect body mass to decrease by about 203 grams, is what that model is saying. Now, this model does have some utility. It's indicating that build depth has some explanatory value in explaining penguin body mass. The adjusted R squared or the R squared values are reasonable for a simple linear regression model here. They're not outstanding by any means, but just accounting for differences in build depth, we're able to account for around 22% of the variation in penguin body mass. And just for completeness sake, I suppose we can take a look at the sigma value. As a reminder, the sigma value is measuring your average prediction error on the training data. So this is like the standard deviation in your model's prediction errors. So this is indicating that when our model makes a prediction, that prediction is going to be off on average by about 723 grams plus or minus. All right, let's move on. So here's some more information that I've hid from you up until this point. So I've colored the dots in the scatter plot according to species. And once we account for differences in species, we can see that this negatively sloped model doesn't really capture what's going on. It is the case that as penguin build depth increases, body mass generally increases as well within each species. So once we start accounting for species differences, the relationship between body mass and build depth changes. And so we're going to try to capture those ideas today. So we're going to start by revisiting ANOVA, analysis of variance, and viewing it as a linear regression model. We're going to look at strategies for using categorical predictors in a model. We're going to look at ordinal scorings versus one-hot encodings and dummy encodings. We'll consider feature engineering steps in recipes. We've seen this once before, but we haven't really used it for anything meaningful. We used it to remove features from a model, but we're going to see more of these step functions today. We'll talk about handling unknown or new levels of a categorical variable. So novel levels means new, previously unseen levels. We'll look at fitting a model with categorical and numerical variables in it. We'll interpret that model, and then we'll kind of leave it there. I'll show you a few more things that you can do with that model once you have it, including making predictions, plotting predictions, including confidence intervals and prediction intervals like we've seen before. So let's get started. As usual with these YouTube videos, I'm going to skip the playing along slides, but you should play along. You can pause and work with your own data if you like. So I'm going to skip through that. And let's take a look at analysis of variance again. It may have been a long time since you last saw an ANOVA test. But what ANOVA does is it allows us to compare population means across multiple groups, multiple meaning 3 or more. And so we may wonder, does penguin body mass vary by species? And the hypotheses for that are that so the null hypothesis is that the average body mass is the same across all 3 species, the adelies, the chinstraps, and the gentoos. And the alternative hypothesis to that is just that at least one species has a different average body mass. Here's a box plot showing the body masses on the training data, and we can see that the gentoos do seem to have a larger body mass visually. The chinstrap penguins and adelie penguins are similar to one another. So we can construct an analysis of variance. This is not using the tidy models framework. It's not using a true linear regression model at all. So just to revisit, AOV conducts an analysis of variance. Inside of the AOV function goes a formula, just like what we've been seeing here in our course. We want penguin body mass in grams as explained by species. And the data that these variables, or the data frame that these variables are coming from, is in the penguins train data frame. So there's a training data frame behind the scenes here. Once I've run that analysis of variance, I can collect the information about it by piping what I've stored as the ANOVA table into tidy. And tidy gives you more information than ANOVA table on its own would. Again, the ANOVA table gives us lots of useful information. We have a term here. We have identified species as what's separating the groups. We have residuals. Residuals are our errors, again, just like with a model. What the residuals here are measuring, though, is a deviation from the group mean. The degrees of freedom due to the groups or due to species here is 2. That's 1 less than the total number of groups we have. Throughout conducting the ANOVA test, we calculate sum of squared values, mean squared values. We calculate an F statistic. Not going to go over any of that here because that's not the point of this discussion. But again, just like with all of our previous hypothesis tests, we calculate a statistic and use it to find a p-value. That p-value measures the likelihood of observing our data from a reality where the null hypothesis is true. So in a reality where body mass across the 3 species of penguins is identical, the probability that we'd observe data like ours or more extreme than ours is nearly 0. And so that's indicating that our data is not compatible with this null reality. It is more compatible with the alternative one, where at least one of the species has a different average body mass. And again, we saw that in the box plot, but now we have statistical evidence to show that what we're seeing in the box plot is unlikely to be sampling variability or sampling variation. It is very much likely to be a characteristic of the populations as a whole. Let's revisit analysis of variance, but do it as a linear regression model. So again, we're going to ask the question, does penguin body mass vary by species? Instead of using the AOV function, though, now what we're going to do is use our at least more recently familiar tidy models framework. So if we're going to do this, we're proposing a model that's going to predict expected body mass using some intercept and then maybe a slope times species. But again, multiplying that slope times species like Adelie or Gentoo is going to pose some problems. So we need to figure out what actually is going to go here. Before we do it, here's a model-based test associated with this analysis of variance, and you'll notice that the results are the same. So the p-value is still nearly 0, degrees of freedom still 2, and the statistic is still 264.6767. So linear regression can be used to run an analysis of variance. Here are the model terms, which may give us a little bit of insight into what the actual structure of this model is going to be. So I've got not just one term, one variable term here. I've got two of them. I've got one for the species being chinstrap and one for the species being Gentoo. We're going to circle back to this later, but the model, again, now that's suggested by this table output at the bottom is one that has an intercept and then a coefficient times species chinstrap and another coefficient times species Gentoo. Even though there was just one variable or one explanatory variable in this model, it was species. We needed some way to encode all of the different species in the penguins data set. Here's what our fitted model suggests. So all I've done is I've extracted the estimated coefficient values, those estimated beta values from the table. That expected body mass now is given by about 3,704 minus 18.45 times species chinstrap plus 1,298.23 times species Gentoo. I've plotted the individual observations here. That's what the dots are. So I've got a bunch of Adelie penguins, each represented by a dot. The higher the dot on the y-axis, the more massive the penguin is. Similar for chinstrap and Gentoos. The horizontal bars through the midsection of the scatter plots is the model's predicted body mass. So this red one corresponds to the Adelies. That is going to be this 3,703.95 value. Once I move to chinstrap, I have a very similar predicted body mass, just slightly lower. This 18.45 is an adjustment on the 3,703.95. And similarly, now over to the Gentoos, much higher body mass on average. And this 1298.23 is, again, an adjustment to that baseline value. The baseline value here corresponds to the Adelies. We can also assess some of the uncertainty associated with these predictions by exploiting the standard error in the model coefficients. So if I do that, I can open up a band around that average body mass indicator that shows us a little bit about that uncertainty. And we can see that average body mass for Adelies and chinstraps do overlap, while average body mass for Gentoos is pretty far set apart from these others. Okay. So let's take a few steps back and let's look at how this linear regression model was actually built and how it used the species as a categorical predictor, or how it manipulated that predictor before using it as components in its model. So again, linear regression models depend on multiplication and addition, which are not meaningful for categories like Adelie or Gentoo, or the island variable, Torgerson, or colors. So we couldn't really fit a model that predicted expected body mass as some intercept plus some slope on species, at least not in the native form. So we couldn't really evaluate this model for a chinstrap penguin. Again, because of what we've been saying, multiplying chinstrap by some number and adding it to some other number is not meaningful. So we need some way to convert categories into numeric quantities that our model can consume and utilize. And there are a handful of strategies that are commonly used. The first one I'm going to show you is one that I rarely use. It requires quite a bit of expertise. We could use an ordinal scoring method, but this would really require some heavy-duty advanced knowledge of penguin anatomy and physiology. But it would be reasonable, perhaps, to score these as an ordering. So we could assign Adelie a score of 1, Chinstrap a score of 2, and Gentoo a score of 3. There are some advantages to this. Under this scoring mechanism, there's only one beta coefficient required for the inclusion of this categorical predictor. That immediately makes our model simpler. It makes the model easier to interpret in some sense. This also can accommodate rankings between levels, but that advantage of accommodating rankings, can also be a disadvantage because it imposes an ordering on the categories and it enforces relationships between effect size. So in this scenario, the effect of being Gentoo on body mass, that score is 3 times the effect of being Adelie. It also means that the expected difference in body mass between Adelie and chinstrap penguins is the same. So the difference here in score is 1. So that difference is the same. The difference in the expected body mass between these two species is the same as the expected difference in body mass between these two because their difference in score is 1. That, and we've seen visual evidence, is not realistic. And so an alternative to scoring is to use dummy or indicator variables to encode each category. So we could do this by creating a new column for each species in our data set. So I've got a column for species Adelie, species chinstrap, and species Gentoo. Each of these indicator variables is like a light switch that can be turned off or turned on. Turning it off is indicated by a 0, and turning it on is indicated by a 1. We can see that the first penguin here is the Gentoo species, and I've got a 1 underneath the species Gentoo column. Second penguin is an Adelie, and similarly, I've got a 1 underneath that column. And so on and so on. This is actually more information than we need, though. So this supplies what people might call a one-hot encoding of the species variable. You can think of these as wires conducting electricity, where 2 of the wires at all times are cold and 1 of them is hot, indicating that yes, I belong to this species. This is enough. We don't need the species variable any longer. In fact, we don't even need every one of those indicator columns either. And so in this first row, I can see that the species of the penguin is not a chinstrap, it is a Gentoo. In the second row of the table, I can see that this penguin is not a chinstrap and it's not a Gentoo. Because there are only 3 species of penguin in our data set, it must be an Adelie. This is an advantage because dropping a column in your data set removes the need for 1 extra beta coefficient. So we can have fewer coefficients by using this dummy encoding. And the dummy encoding, again, really does recapture the actual species of the penguin from the original data set. A 1 underneath a column indicates the penguin belongs to that species. So like this first penguin is a Gentoo, and we see over in the species column it's a Gentoo. And the last penguin here, we see a 1 in the chinstrap column. the species is a chinstrap penguin. And here in the second row, where both of those species indicators are zeros, this must mean that I am the base level or the leftover category Adelie. So there's a few advantages to this, and it's that it can model variable effect sizes between levels, so we're not forcing proportionality anymore. We don't have to have a ranking between categories before we provide the data to the model. The disadvantage here is that it requires more beta coefficients. We need one less than the number of unique levels for that categorical variable. So here we're trying to encode species. There were 3 species in the data set. We need 2 columns to encode all 3 of those species via indicator variables. All right. So again, I'm going to skip through the try it, but if you have some data that you're working with, please try out this idea of encoding categorical predictors with your data. So back to our model from earlier, this output seems to make more sense. So I have an intercept. I have a model term attached to species chinstrap. That's going to be an indicator variable that takes on the value 0 if the penguin is not a chinstrap penguin. And it'll take on the value 1 if the penguin is a chinstrap. Similar for the species gen2 variable, it will take on either 0 or 1. So I've got now this equation, this fitted model or estimated model for penguin body mass. This is the same model as we saw earlier. Baseline body mass is 3703.95 grams. This would be the body mass of a penguin where species chinstrap takes on the value 0 and species gen2 takes on the value 0. And so if the penguin is not a chinstrap and is not a gen2, then it's the leftover category. It's an Adelie. So the Adelie penguins, we expect to have a body mass of around 3,704 grams. These other terms indicate adjustments, and so the prediction for a chinstrap penguin, now the species chinstrap variable turns on, species gen2 is turned off. We get an adjustment downward on the expected body mass, so just below 3,700 grams this time. And similar for species, for the gen2 species, now species chinstrap, that term gets turned off, it takes on the value 0. And species gen2 is turned on, it takes on the value 1, adding that extra 1,398 grams to the penguin body mass, indicating that gen2s are much larger than the other 2 species of penguins with an expected body mass just over 5,100 grams. And so I want to be careful here. I want to highlight that the interpretations for these beta coefficients on dummy variables are not slopes. We can't talk about what happens if species chinstrap increases by 1 because it's not a thing that increases or decreases. These are direct adjustments to the expected body mass, accounting for differences in the species. And so the negative 18.45 here is an adjustment. It's indicating that if we have 2 penguins, one is an Adelie because it's the base level, and another one is a chinstrap, we expect the chinstrap penguin to be slightly less massive than the Adelie penguin by about 18.5 grams. All right. So let's look at the code required to include categorical predictors with the tidy models framework. This is again, one of the first times that we're seeing an actual feature engineering step. So we're taking a variable or a feature in our data set, and we're changing how it's going to be used inside of the model. We'll encounter lots of feature engineering steps throughout our course. These feature engineering steps are appended to our recipe. That's where we're going to add them. So if we wanted to build the linear regression version of our ANOVA test, this is the code required to do it. So ANOVA is a subset of a linear regression model. So I'm going to take a linear regression model, set the engine to LM like we usually do, and I'm going to call this the ANOVA specification. There's nothing special about that again. The recipe that I'm going to use is to predict body mass using species as the only predictor. Now, species is categorical, so I have 3 groups, one for each species, and I'm wondering if body mass is associated with the groups, if it changes across the groups. So that really is an ANOVA test. Just like with all our previous recipes, we have to declare where R can find the data. Those columns are available in the Penguins train data set. But now something new. We're going to pipe that recipe into a feature engineering step. We can pipe into as many feature engineering steps as we want. This feature engineering step is called step dummy, and this is going to get those dummy indicator variables for our species. By default, this is going to give us base level. That base level is going to be determined by alphabetical order. So the first category to appear in alphabetical order will be the base level. That category will not appear as a term in our model. All of the other categories will appear in our model, and those beta coefficients will be adjustments up or down from that base level. As usual, after creating a model specification and a recipe, I package these two things together into a workflow, and then I fit the model to the training data. All right. So again, you can try this with your own data, whether it's the bike share data, the Airbnb Europe data, or another data set. Let's do something slightly more interesting here. We'll build a model that better corresponds to the plot that we began this video with. So this plot, identifies the species type, but it also identifies a potential association between build depth and body mass. And we can see that within each species, it seems to be the case that as build depth increases, so does body mass. That's true for the gentoos up here in the top left corner, and it also seems to be true for the chinstrap and Adelie penguins here in the lower right. So let's build a model that accommodates both build depth in millimeters, a numeric variable, and species, a categorical variable here. So we'll start with our model specification just like usual. There's nothing different here. Our recipe, again, we'll start like usual and include this step dummy feature engineering step so that we can handle the species variable. But this is saying now I want to predict penguin body mass. I want to use build depth in millimeters and species as explanatory variables for this. So now I'm going to include both pieces of information. This will allow us to model species by species relationships between penguin body mass and build depth. After doing this, we're going to package both the model and that recipe together into a workflow just like usual, and we'll fit that workflow to the training data. So again, not much is new here. It's just that now that we're including a categorical variable as one of our predictors, we should be using step dummy to take that categorical variable and take its levels and convert them into numeric values that can be consumed or used within a linear regression model. All right. There are some common concerns when you're using categorical predictors. I'm going to give you those concerns and some ways to fix them here, and I'll give you some other feature engineering steps later on in the summary that you might be interested in using. So if you have missing values, you can fill in those missing values with a feature engineering step called step unknown. Inside of step unknown goes the name of your categorical variable. So here it would be species. And this would handle any penguin where the species was not known. It would create a new category called unknown. It also could be the case that you encounter a record or an observation where the category that it belongs to is new. That category was unseen during training time. If that happens, your model will crash because it doesn't know how to handle that new category. So you can use step novel with your categorical variable name, so species here, to reassign new classes into an umbrella class called novel. Hey, this is something I haven't seen before. And one more thing you can do, this is going to be particularly useful when you have a categorical variable with lots of different levels underneath it, some perhaps quite small. Step other. You can combine rare classes into a class called other here. This is useful for grouping classes together. The order in which you use these matters. So step unknown, step novel, and step other all assume that you're dealing with the raw categorical variable that still has its levels underneath it. Once you use step dummy, you no longer have that categorical variable in your data set. You have the indicator columns instead. So if you use any of these three functions, you should use them before hitting step dummy. So the order of the feature engineering steps in your recipe pipeline matter. All right. So we can assess this new model. Here's a global test for model utility. The p-value here is near 0. It's being rounded to 0. That's indicating that our model has some good things in it. Our model has something useful for explaining differences in penguin body mass. And we've got our individual term-based tests here as well. I've added inside of tidy this confint equals true to give me these two extra columns, conf low and conf high. These are on the estimated model coefficients. So rather than constructing them by hand, this does it for us. All right. So controlling for differences in build depth. So we know that penguins are going to have build depth differences. It does look like Gen 2s, because of their small p-value, have statistically different body masses than Adelie penguins. However, because the p-value here attached to chinstrap penguins is so high, this indicates that even controlling for differences in build depth, chinstrap penguins and Adelie penguins may not have different body masses. We were able to estimate a difference, but we're not able to claim that that difference is not 0. If you look at the confidence interval for that coefficient, it contains both negative numbers and positive numbers, so it also contains 0. So 0 is a plausible coefficient there. Still, we are able to extract our estimated model from this table. So we get negative 912.91 as our intercept. Remember, this is not meaningful because it would correspond to an Adelie penguin now, that base level penguin, with a 0 build depth. And we have no penguins with 0 build depth. All right. Let's take a look at a side-by-side of our models. So on the left here, we have the species-only model. On the right, we have the model that accounts for both species and build depth. We can see that the adjusted R-squared is higher on, I didn't intend for all that to get highlighted. The adjusted R-squared is higher on this model that accounts for both species and build depth. And it's higher by quite a bit. We've gained 12 percentage points there. That's great. And our sigma value has dropped by quite a bit as well. It's dropped by nearly 100 grams. So we got huge improvement just by accounting for species. All right. Earlier I had talked about that chin strap coefficient potentially being 0. It's useful to be able to visualize these, and I gave you some code for how to visualize it in the slide deck. So you can take a look at the code that I use. This is largely something that you can copy and paste. So here we've got a picture of the model coefficients. We can see that the coefficient on the Gen 2 species is very large, and it doesn't overlap with 0 at all. The coefficient on build depth is not as large, but its confidence interval doesn't overlap 0 either. And the coefficient on chin strap has significant uncertainty associated with it, and that uncertainty does include the possibility of that coefficient being 0. Again, what that indicates is even though we're accounting for differences in build depth, we don't have statistically significant evidence to suggest that chin strap penguins and Adelie penguins have different body masses. All right. We can interpret the model just like we would interpret any other model. It's just now that we're going to have to be careful with our interpretations of these dummy variables, the species chin strap and species Gentoo. So the intercept, again, it's not meaningful. It would correspond to a penguin with a build depth of 0 millimeters. And in fact, it would correspond to an Adelie penguin whose build depth is 0 millimeters. The build depth coefficient, so if I'm looking at this term now, controlling for differences across the species, we expect a 1 millimeter increase in build depth, so that's a 1 unit increase in build depth, to be associated with about an increase of 252.34 grams in body mass on average. You'll notice that this is the same across all of the species, and we'll look later at how to account for the fact that the relationship between build depth and body mass may actually depend on the species of the penguin. But for now, the relationship between build depth and body mass is independent of species. When we look at the chin strap coefficient here, we can say that given a chin strap and an Adelie penguin with the same build depth, so this value has to be the same, we would expect the chin strap penguin to be slightly less massive. It'll be lighter by 23.37 grams. This, though, is not statistically discernible, and so it may actually be the case that they're the same. They have the same mass, or even the case that the chin strap is larger or more massive than the Adelie. The Gentoos, though, do have a statistically significant difference. We can see that here with the very small p-value. So given a Gentoo and an Adelie penguin, again, we're comparing to the Adelies because Adelie is the base level. It's the one that's not appearing in our model. So given a Gentoo and an Adelie with the same build depth, we expect the Gentoo to have greater mass by about 2,222.1 grams on average. So again, these coefficients on these species indicators are not slopes. They're direct adjustments due to the category that I belong to. All right. Again, just a note here, some of these comparisons are misleading because Adelie build depths rarely overlap with the Gentoo's build depths. Gentoos had much more shallow bills than the other two species of penguin did. Okay. This is all now sort of additional stuff that you may be interested in using or exploring. So we can make predictions with this new model. If we're going to make predictions, we're going to need to have information about the build depth of a penguin and about the species of a penguin. What I'm doing in these lines of code, I think I highlight, we'll get rid of everything else. What I'm doing in these lines of code is I'm taking the build depth and I'm creating 250 different values between 13.1 and 21.5. This is the most shallow beak, and this is the deepest beak. So I'm creating just a range of values here. And then for species, I'm creating the 3 species that we had in our data set. And what crossing is going to do is it's going to take all of these build depths that we created and assign them to each of the 3 penguins. All right. In fact, I think I'm going to do a small example here just to show you what's happening. So I'm just going to load the tidyverse because I need that to use the crossing function. I'm going to create an object called ABC. It's going to have A, B, and C in it. I'm going to create a new object called 1, 2, and it's going to have just 1 and 2 in it. So I'm going to create both of those objects. Now if I use crossing, and I use letters equals ABC, and numbers equals 1, 2, what's going to come back is I'm going to see a data frame where A is next to 1 and A is next to 2. And then B is next to 1 and B is next to 2. And C is next to 1 and C is next to 2. And so we can see that we've created all combinations of A, B, C, and 1, 2. That's what crossing is doing. It's just doing it on a larger scale here. Now, what we're going to do is we're going to take our fitted model object. So this is the model that we created. It uses build depth and species. We're going to augment our new data. That new data is the new data that we just defined above. It's all of the combinations of build depths with the 3 different species. We're going to take that augmented data frame and we're going to attach more to it. So this is really just for plotting purposes. So augmenting the new data gives me one new column. It gives me a .pred column. Next, I'm going to add more to it. I'm going to take my model and I'm going to use the predict function instead of augment. Predict is a little bit more flexible, but it gives you less information back. It only gives you back your predictions. I'm going to predict on my new data. So this is all these penguins again. And the type of prediction I'm going to make is a confidence interval. So again, coming out of these 2 lines is going to be a new data frame, but predict does not give me back my original data. I'm just going to get a new column called pred lower. That's the lower bound for my confidence interval, and pred upper, which is the upper bound for my confidence interval. I don't like pred lower and pred upper as names, especially because we're going to have prediction intervals. This is a confidence interval. So I'm going to rename those. So I'm going to take the pred lower column and I'm going to make it called conf lower. I'm going to take the pred upper column and I'm going to rename it as conf upper. So now I know these are confidence interval bounds. So all of this, again, I'm taking my fitted model object, I'm making predictions on my new data. Out of the predict function only comes now a lower bound and an upper bound for the confidence interval that I'm asking for. Those aren't named what I'd like them to be named by default, so I'm going to rename them so that they better reflect what they actually are, the lower and upper bound for confidence intervals. So at this point, I have my original new data. It has penguin build depths crossed with the species type. I've used augment to add my model's predictions to that. So I get a new .pred column. I've used these few lines of code to bind on new columns. So I'm taking new columns and I'm just attaching them to my existing data frame. Those 2 new columns are the lower bound and upper bound for confidence intervals for my model predictions. And then I'm going to do one more thing. It's basically the same as what I did before, but I'm attaching now prediction intervals to that. So I'm adding 2 more columns to my data frame. These are now going to be pred lower and pred upper. Those are named appropriately already, so I'm not going to bother renaming them. So all of this is going to get me a new data set with all different combinations of species and build depths. I'm going to get predicted body mass for each of those penguins. I'm going to get confidence interval bounds for the body masses for the average penguin of each species at each build depth threshold. And I'm going to get prediction intervals or prediction interval bounds for individual penguins of each species at each build depth. And so now we can plot that. So I've created this data frame of predictions. It contains 3 pieces of information that I'm really interested in, or 3 things that I'd like to plot. It's the model predictions, it's the confidence bounds, and it's the uh, prediction interval bounds. So at this point, I'm going to make a plot. I'm starting with ggplot straight away rather than piping data into it. We want to do that because we're switching what data we're plotting across these levels. In particular, this last level is using a different data set. It's using the training data. That's what I'm going to use to plot my original penguin body masses and build depths. So I'm going to start with ggplot. That's taking out a canvas to draw on top of. I'm going to add a layer to that. I'm going to use geom ribbon, which is going to give me a band that's colored in between some lower value and upper value. So I have the X location for a cross section of that band. So I'm going to plot build depth in millimeters along my horizontal axis. And then I want a band stretching from the lower bound for my prediction interval all the way up to the upper bound for my prediction interval. So I'm going to get a band of values here where I think the penguin body mass will live at a particular threshold for build depth. And then I'm going to make this slightly, or quite a bit transparent. Next, I'm going to do the same thing, but I'm going to plot my confidence interval. So my confidence bounds, my minimum y value is conf lower, my maximum y value is conf upper. I'm using slightly less transparency here. These are numbers that you can just play around with and see what you like and what you don't like. So at this point, I have a plot. I've added to it prediction intervals. Remember, those are for individual penguin body masses. So this is going to be a wide ribbon. I've added to that a ribbon for confidence intervals. This is for the average penguin body mass. So this ribbon is going to be much more narrow because I get to use unusually large penguins and unusually small penguins to cancel one another out. On top of that, I'm going to add a line. This line is going to be my model's predictions. I'm going to use build depth in millimeters as the horizontal location. You'll notice that's consistent across all of the layers in this plot. It should be. The height of that line is going to be the predicted values. And I'm going to color the line by species, which is going to give me one line for each species in my data set. LWD is governing the thickness of the line. 1.25 is saying I want this 125% of the default thickness. So this is making it a little bit thicker than the default line is. So this is adding a line representing my model to my plot. And then last actual layer going on here, I'm going to add a scatter plot, geom point, with my training data on it. So this is the actual build depths and the actual body masses. And I'm going to color each of those points in by species. So again, we have a plot. We added a band of prediction intervals. We added a band of confidence intervals, and we added our model. Then on top of all of that, we added a scatter plot representing our original training penguins. Now we're going to label the plot. So I've got an X and a Y axis label. I'm going to facet this out so that I can see each species individually. So facet wrap breaks your plots up by category. Tilde species here means I want one plot for each species. So I want my plots as explained by species. And then ncol equals 3 says I want 3 columns in the plot output. So I want each species side by side here. And then because I'm coloring by species in the plot, I'm by default going to get a legend, and I don't want that legend. So I'm just going to suppress it here by setting the legend position to none. Again, this is largely something that you can copy paste and adapt. You won't always be dealing with build depth or with body mass. So there are some things that you'll have to change. And here's our model's predictions. It's a nice visual that shows how well our model is doing in some cases, and actually places where maybe our model can be improved. So we see a positively sloped relationship in all three plot panels. We also see that the slope of the line in each panel is the same, and that's an artifact or a characteristic of the model form we proposed. We're accounting for differences in species, but we're using we're using build depth in the same way with each species. And so we're not able to account for different relationships there. Okay. So what we got back was a new model, but that model is not one line anymore. It is three separate parallel lines. All right. We're almost done here. I want to talk just a little bit about some additional feature engineering steps for categorical predictors. So we saw step unknown. Step unknown will create a level for unknown values. If we expect to encounter missing values, there are a bunch of functions from this impute class. These impute feature engineering functions will allow us to take a best guess at what a missing value is. There are lots and lots of different strategies available to us. Step impute mode can be used with categorical data. Mode is the most often appearing category. So step impute mode would just take a missing value for species or any categorical variable you want and put in the most frequent category there. Just saying, well, if you're making me guess, the most popular category is the one that I'm going to guess. We saw step novel for encountering new levels of a categorical variable. This will happen, especially when you're dealing with a data set that has lots of categories underneath a categorical variable, so lots of observed levels. So you may want to use that step to protect yourself. And step other, we mentioned earlier today too. If you expect to have lots and lots of levels, especially some where they're infrequently observed, so they're rare categories, you can group those levels together into an other level with step other. This is pretty good practice because if you have small categories, then each of those observations in that small category have really heavy influence on your overall model. And that puts you at risk of overfitting because individual observations have heavy, heavy influence. All right, and that's it. So in summary for today's video, we can include categorical predictors in a model to differentiate predictions across the levels of that variable. Including categorical predictors requires that we have some sort of an encoding scheme in order to convert those levels to numeric values. And we saw two of them, even though we only used one today. Scoring assigns a distinct number to each category. I generally stay away from this method because it requires some real strong content knowledge, some real strong expertise in the domain that you're working within, because the scoring does two things. It imposes an ordering on your categories, and it imposes proportional differences in the effect from one category to the next, which is often not something we want to do. You can implement scoring, even though we didn't do it in this notebook, by adding step ordinal score as a feature engineering step instead of step dummy. We use dummy encodings today to replace a categorical predictor with a collection of binary 0-1 variables indicating the levels of that categorical predictor. This is something that I use often, and I recommend that you'll use it also. You use these dummy encodings by adding step dummy as a feature engineering step in your recipe. So you just pipe that initial recipe line to step dummy. You can include as many feature engineering steps in your recipe as you'd like. This is just the first real feature engineering step that we're encountering. In case of rare levels, you may also want to include things like step other, step unknown, or step novel as part of your recipe as well. A warning here though, the order in which you apply these things matters. At a bare minimum, step dummy has to come after you're using these. You can't use it before, because once you've used step dummy, you no longer have your categorical variable. You have the dummy indicator encodings instead. And then we saw again today that a linear regression model, including a single categorical variable as the sole predictor, is equivalent to an ANOVA test, an analysis of variance, comparing multiple group means across one another. For a linear regression model with at least one numerical predictor, the result of the inclusion of a categorical variable in the model is a shift in the intercept. That's a vertical shift for each one of the levels of that categorical predictor. That's the impact that including the categorical predictor had on our model today. All right. Next time, we've lost a few class meetings, so what we're going to do next time is we'll talk about higher order terms. We'll talk about interactions, and then we'll also talk about, at a separate class meeting, higher order terms by adding curvature to our models. All right, that's all for now. Thanks, everybody. I'll see you next time.